Hello, everybody. Welcome. Welcome to the first lesson of this course, which is an introduction to quantum computing. Now, in this lesson, I'm going to be talking about the foundational concepts of quantum computing. Like, what is it? What is so special about it? And what makes it so different from traditional computers? I would not recommend skipping this course, skipping this lesson, specifically because it forms the foundation. Before you learn about security of quantum computing and what are the risks, you first need to understand what it is. And I've seen a lot of people, they think they know what quantum computing is and how it works, but they really, they just have a very superficial understanding. So that's what the point of this lesson is. So in this lesson, we're going to be covering what is quantum computing specifically, how it differs from traditional computing. And in the second part of this lesson, I'm going to be covering what are the key concepts you should understand, right? So, like I've said before, what is quantum computing? So, quantum computing, like I said, it's like an emerging field of computing, and it draws upon different concepts from a traditional computer. It takes advantage of the quantum world, which is enables a bit of data to act as both a 0 and 1 at the same time. And what's the big deal about that? Okay, so it can think of 0 and 1 at the same time. Well, the point is it gives it the power to make calculations that would be impossible for a traditional computer to make. And once quantum computers like become mainstream, they will be able to sift through potential solutions to a problem simultaneously, zeroing in on the correct answer very, very quickly. And this sort of sifting through multiple things simultaneously, that's a thing traditional computers they cannot do very quickly. They can do, let's be to be very, very clear, they can do, but they cannot do it very, very quickly. And if there are millions and millions of different possible paths available, they will take too long. It's simply not doable with a traditional computer. So this is what we talked about earlier. If you remember, this is what a classical computer looks like, right? It's binary, as in 0 and 1. It thinks about data as it can be either be 0 or a 1. And how does quantum computing differ from traditional computing? So traditional computing, if we look at, it relies on, like we're talking about our standard computers, right? Our laptops, desktops, smartphones, or servers, and they work by processing information using algorithms. However, as powerful as these machines are, they have limitations on how much information they can process. And these limits, they are very, very noticeable when you try to solve highly complex problems. Like for example, you're simulating molecular interactions or trying to break advanced algorithms like encryption, right? And this is where quantum computing comes into play. It's so I want to be very clear. Quantum computing is not just about doing things faster. It's about doing things in a way that classical computers simply cannot do. The way quantum computers operate is fundamentally different from traditional computing. So instead of processing information in the way that we're used to, it utilizes the laws of quantum mechanics. And this is where it gets interesting. So instead of using data like 0 and 1, like we say, they talk about qubits, which is 0 and 1. So to explain this visually, I want you to think about trying to solve a maze, right? You have multiple pathways available. A classical computer would try to solve every possible path one at a time, right? Flipping between zeros and ones to find the correct path. A quantum computer, on the other hand, it could explore all the paths simultaneously because of the way qubits work and this ability to handle many, many possibilities at the same time. This is the reason quantum computers are able to outperform. So while quantum computers still have their place, they are very, very efficient. That where operations are required that involve a large number of operations, right? Like tasks that involve a large number of operations, they're still limited by their binary approach. And while quantum computing, because of qubits, they are very, very exciting for fields in science, cryptography, AI, where the challenges we face are becoming very, very complicated, right? And the potential here is enormous. And while we are still in the very, very early stages of quantum computing, it's very, very clear this is going to be a massive, massive leap forward for computing technology, even more than AI, I would say. So this is what I talked about. I'm not going to repeat this, but yeah, this is basically, we talked about zeros and ones, and quantum computing can exist in like two states at the same time, 0 or 1 at the same time, right? And let's talk about this. So what are the differences from traditional computing, right? So like I said, these are the computers we use in our everyday lives, right? PCs, laptops, smartphones, and they process data in a logical and sequential manner, one step at a time in an orderly fashion. And this makes it excellent for a large variety of tasks, right? But they're not suited for large scale complex tasks. And because of quantum computing, they're used by very specialized tasks, very experimental hardware, and they can process data at the same time. Like I gave you the example before, like a not traditional computer would try to solve a puzzle one by one, right? Very, very fast, but still one by one. Whereas a quantum computing would use all the different possibilities at the same time. And of course, the advantages here are amazing, right? They can solve very, very complex problems, and we're going to take a look at that. A quantum computer can solve things that a traditional computer might take thousands and thousands of years, and that is just blows my mind when you think about it. And you can think about the industries where this can think, like finance. You can improve the speed and accuracy of your financial risk predictions for banks, right? Because you can run simulations, you can detect fraud. For healthcare, like pharmaceuticals, you can do drug discovery and development significantly faster, right? And you can analyze so huge amounts of data for faster disease diagnosis. And like if you want to talk about security, you can transform security by looking at further strengthening encryption algorithms. You can identify and respond to vulnerabilities in real time because of the speed in which they work, right? And on and on. I mean, I can go on. Like AI and machine learning, they need huge amounts of processing power. So literally every field that is available, it will get impacted one way or another with quantum computing, right? And at the same time, we have to be very, very clear, there are limitations. So quantum computing is not just everything is hunky dory. No, that's not how it works, right? Quantum computing has limitations also. For example, cooling. Quantum computers require extremely low temperatures to function, and the qubits, they are incredibly sensitive. They can get well, like very easily disrupted by heat or electromagnetic radiation. And to keep qubits stable and allow them to work as intended, they often used to be need to be keep at very, very low temperatures, right? And keeping them at a very, very low temperature, it often requires very, very expensive and complex machinery. So you need to have that thing in mind. Error correction. Quantum computers are much more prone to error than traditional computers. That's why they're not suited for every task. And unlike traditional computers where information is relatively stable, qubits are very, very sensitive to the surroundings. Like they can change. So the chances of error are very, very high. So you have to keep that into mind also. Expertise. Quantum computer requires specialized knowledge in both quantum computing and computer science. And building and operating quantum computers, it requires a high level of expertise. And it's not like uh, whereas you have engineers and computer engineers, quantum computing is still an emerging field, and the pool of experts is very, very small. So the need for upskilling and getting the required people, they're still there. And apart from that, there are other challenges also, like scalability. So building quantum computers that can scale from a few dozen qubits to say 1,000 or 1,000,000 qubits, that's a huge technical challenge. Stability, like I said, qubits need to maintain their quantum states long enough. They get disrupted very, very fast. And of course, cost. The cost of research, development, and building quantum computers is very, very high, which makes it harder for smaller companies or researchers to do work because they need huge amounts of funding. So, in conclusion, quantum computing is amazing, but it faces major, major challenges which have to be taken into account. And that brings me to my next point, which is, will traditional computing fade away? The answer is no. If you're thinking that quantum computers, once they become mainstream, everybody's going to be having a quantum computer on their laptop, no. Realistically speaking, they're not going to replace traditional computers. In fact, for most tasks, quantum computing are far less efficient than the computers that we use today. Think of them like graphic cards. If you have graphic cards, they're highly specialized tools designed for specific types of computations and not general purpose work, right? So, quantum computers is going to complement classical computers and not replace them. And because quantum computers are used for very complex and challenging problems that computers are facing, and that is where they excel at, like climate modeling, drug discovery, financial optimization, space exploration, those big, big problems. For everyday tasks like browsing the web to running applications, your traditional computers are not going to go away. They will come into play for uh, what do you call very, very complex and structured problems. That's what I wanted to you to think about. So, for example, if you're searching a database, a traditional computer, this is what you will need it for, right? You would not need to use a quantum computing for. But for example, if you want to simulate the behavior of a molecule, they can be millions and millions of variations there. So this is where quantum computing will into play. So you need to model the behavior of a complex molecule to understand its like chemical properties, how it interacts with other molecules, and this is crucial in drug discovery, right? So this is where quantum computing really excels. It will simulate all these sort of different scenarios that are there. And this will help you to understand chemical reactions, discover new drugs, or design advanced materials. So I hope this give you a good understanding of a very, very good foundational understanding of quantum computing. In the part two, I'm going to talk about some of the key concepts. This part is optional. You don't need to deep dive into the technicalities of quantum computing to understand the risks. I would recommend it. So it's completely up to you. So thank you very much, and I'll see you in the next lesson.